We end tonight with the clearest pictures yet of Neptune, the most distant planet in our solar system.
We're looking at Neptune's orbit, and it's not following Newton's laws.
For centuries, Neptune sat quietly at the edge of our planetary system, a remote, icy world cloaked in a sapphire haze. Known as the eighth planet from the Sun, Neptune was long thought to be a settled mystery, a cold gas giant, swirling with storms and whipped by the fastest winds in the solar system. But now, all of that is being challenged. In a moment that left even seasoned astronomers speechless, renowned astrophysicist Neil deGrasse Tyson delivered a presentation that may reshape everything we thought we knew about Neptune, and possibly about planetary formation itself. The announcement took place during a major international symposium, where scientists gathered to discuss new findings from the James Webb Space Telescope and other cutting-edge instruments. What began as a routine analysis quickly turned into a stunning revelation. Tyson, known for his gift in translating complex cosmic concepts, laid out a story that defies our traditional understanding of gas giants. For over 170 years, Neptune has been part of the scientific lexicon, its existence first predicted mathematically due to peculiarities in Uranus's orbit. And aside from Voyager 2's brief flyby in 1989, we've only had telescope data to work with. What little we did know was that Neptune had violent weather systems, a strangely tilted magnetic field, and a reputation for being cold, distant, and mysterious. But that mystery just deepened. According to Tyson, recent high-resolution data gathered by JWST and powerful Earth-based interferometers have revealed that Neptune is far more complex, and potentially more unstable, than previously imagined. The most significant surprise came from within. Neptune's internal structure appears to be anything but simple. Rather than a smooth gradient from gas to ice to rock, new measurements suggest a chaotic layering system of strange, plasma-like substances interacting in unpredictable ways. These findings hint at swirling regions of anomalous heat far beneath the clouds. Heat that should not exist at such a distant point from the Sun. Traditional models assume Neptune gets its limited heat from solar radiation and residual formation energy. But the newly discovered thermal signatures suggest an active internal mechanism, something generating heat from within, without any obvious trigger. And that's not all. Neptune's magnetic field, already unusual in that it is not centered and dramatically tilted, appears to be changing. Its magnetic heartbeat shows signs of drifting in a cyclical fashion, with magnetic poles that seem to fluctuate in a way never before observed in a planet. This implies that Neptune's magnetic field may not be generated by a standard liquid metallic core like Earth's, but perhaps by an exotic shell of electrically active ices undergoing unknown chemical transformations under immense pressure. This brings us to the most unsettling idea of all, that Neptune might contain cavities or layers that behave more like electromagnetic resonance chambers than traditional planetary strata. If true, this would be a complete rewrite of what it means to be a planet, suggesting that Neptune isn't just another gas giant, but an entirely different kind of celestial object. Tyson cautiously floated a theory. Neptune could be a dynamic equilibrium system, a world constantly rebalancing itself from the inside out, with processes we don't fully understand driving both its internal and external phenomena. The implications stretch far beyond Neptune. For one, they call into question the early evolution of our solar system. Neptune's presence and gravity helped shape the Kuiper Belt and may have played a role in ejecting another, now missing giant planet. If Neptune itself is more unstable or exotic than expected, it means the early history of the solar system was far more chaotic than we've modeled. And then there's the radio mystery. Recent detections of deep, rhythmic radio emissions emerging from within Neptune's lower atmosphere don't fit any known pattern. While planetary radio emissions are not new, these signals have peculiar frequency shifts and pulse rates that suggest something deeper is at play. Some researchers speculate these may be natural but unfamiliar phenomena, possibly rooted in quantum-scale interactions happening under pressure regimes we've never replicated on Earth. Even the outermost layers of Neptune may be hiding materials never confirmed in the wild before. The evidence points towards superionic ice, a bizarre phase of matter where water becomes both a solid and a liquid simultaneously. Under extreme pressure, The oxygen atoms form a crystalline lattice while the hydrogen ions move freely like a fluid, creating a slushy electrical conductor. This exotic material could help explain Neptune's surprising thermal activity and fluctuating electromagnetic output. And if those materials exist in abundance, they may even form moving currents beneath Neptune's clouds, acting like conveyor belts for heat and energy. What makes this all the more shocking is the speed and power of Neptune's winds. While we've known about them for decades, new data suggests that their origin may not be atmospheric at all. Instead, they might be driven from deep within, propelled by thermal spikes or strange material phase shifts. In simpler terms, Neptune's storms may be erupting from the inside, not swirling down from above. This fundamentally challenges our weather models. Earth and Jupiter rely on solar heating and rotation to drive weather. But Neptune may be unique, a planet whose meteorology is internally fueled, making it the first known example of such a system. And if Neptune is this strange, what about all those exoplanets we've been calling mini-Neptunes? These are some of the most common types of planets detected in other solar systems. Tyson's argument is clear. If our own Neptune is so different from what we expected, then our assumptions about thousands of similarly sized exoplanets could be wildly inaccurate. Even more provocative was Tyson's brief, but daring reference to failed star models. While Neptune isn't massive enough to ignite fusion and become a true star, its internal energy patterns and strange emissions may point toward a new class of object, something that sits between planet and brown dwarf, a sort of hybrid entity that defies current labels. This isn't just a new chapter in astronomy. It's a new genre entirely. And while we still need further observations to confirm these radical possibilities, one thing is clear. Neptune is not just an icy blue in the night sky. It is now one of the most exciting and least understood worlds in our entire cosmic neighborhood. This revelation has lit a fire under planetary science. Researchers are now calling for dedicated missions to Neptune. Not flybys but orbiters or even atmospheric probes that can dive into its cloud layers and sample the materials firsthand. The urgency is growing. If our own solar system still holds such deeply misunderstood mysteries, what does that say about the galaxy beyond? Neil deGrasse Tyson's revelation wasn't merely about one planet. It was about humility, the realization that even the worlds closest to us can surprise us in the most fundamental ways. It's about curiosity, our insatiable drive to explore, question, and reimagine. And it's about the awe-inspiring complexity of the universe we call home. Neptune is no longer the silent giant at the edge. It has become the voice in the dark, calling us to look deeper, think broader, and never assume we know what lies beneath the surface. The idea that such a distant world, over 4 billion kilometers from the Sun, could harbor internal dynamics more mysterious than Jupiter or Saturn is a humbling realization. Once relegated to a footnote in textbooks, Neptune is now emerging as a key player in unraveling the hidden complexities of planetary science. This dramatic shift is not just due to its sheer distance or extreme conditions but because of what it's now revealing about the limits of human knowledge. Among the most groundbreaking discoveries Tyson shared is the concept that Neptune might possess properties previously attributed only to theoretical bodies. For instance, the internal anomalies suggest it may behave more like a transitional object, something between a conventional planet and a kind of mini-failed star. This defies our understanding of planetary categories, suggesting a spectrum rather than discrete boxes for labeling celestial bodies. The potential for stratified cavities, essentially hollow zones or resonant chambers, inside Neptune introduces a seismic shift in thinking. These aren't just geological quirks. If confirmed, they could be influencing not just the planet's thermal signature but also its magnetic orientation and internal energy cycling. Such cavities may act like tuning forks or amplifiers for magnetic resonance, creating wave-like interactions that ripple across the atmosphere and magnetosphere. Tyson also touched upon the evolving theories regarding superionic ice. This exotic form of water, existing in a state where it behaves like both a solid and a liquid, is now thought to be abundant within Neptune's interior. In this state, the water molecules are compressed to such an extent that their hydrogen atoms are stripped away, forming an electrically conductive medium. These substances may be flowing in complex circuits, driving internal currents that fuel the erratic magnetic field. Moreover, if such materials are prevalent within Neptune, it opens up the possibility that other outer planets, and even exoplanets, could host similar internal chemistries. This radically alters our assumptions about what types of planets might be geologically active, magnetically potent, or even capable of producing complex weather systems driven by internal heat rather than solar input. Another fascinating aspect that Tyson highlighted was Neptune's abnormal heat emission. Standard models predicted a planet with minimal internal heating at such a remote distance from the Sun. Yet Neptune radiates more than twice the energy it receives. It's not supposed to glow, but it does. And not faintly. This implies that something deeper is burning within, not through fusion, but through friction, phase transitions, or possibly quantum processes operating under pressure regimes far beyond anything replicated in laboratories. One intriguing implication is the impact on our understanding of planetary evolution. Most existing models are built on assumptions derived from the inner solar system: Earth, Mars, Venus, and even Jupiter. But what if the outer planets didn't evolve in the same way? What if they followed a radically different path shaped by external migrations, gravitational interactions, and pressure-driven chemical evolution? Neptune's strangeness suggests that not all planets are forged alike, and their internal complexity could be the result of divergent evolutionary forks billions of years ago. And while Neptune's surface and upper atmosphere present a familiar facade, a swirling canvas of methane clouds and high-velocity storms, it's the interior that now appears to be the true frontier. Tyson suggested that Neptune may be self-exciting, with layered internal structures producing pulses of thermal or electromagnetic energy that then rise to the surface, driving atmospheric activity. If true, it would mean that Neptune doesn't just react to its environment, it creates it. This has profound implications for planetary habitability as well. Traditionally, the search for life has focused on terrestrial planets in the so-called Goldilocks zone. Not too hot, not too cold. But Neptune and other ice giants may possess internal environments capable of complex chemical reactions, even if life as we know it cannot exist on the surface. Subsurface environments, perhaps within moons or within Neptune itself, may host warm, chemically rich pockets, incubators for the unexpected. This line of thought also impacts how we interpret exoplanetary data. If Neptune, the prototype for so many mini-Neptune exoplanets, is fundamentally more exotic than previously thought, then perhaps our methods for classifying exoplanets are too simplistic. Thousands of distant worlds have been categorized based on their size and distance from their stars, but these labels may mask internal complexities we've never considered. Tyson urged the astronomical community to develop new models, not just for how planets look, but how they behave internally. One of the more controversial aspects Tyson briefly alluded to was the idea that Neptune's behaviors could resemble processes seen in brown dwarfs, objects too massive to be planets, but not massive enough to sustain hydrogen fusion. While Neptune is not nearly massive enough to qualify, some of its electromagnetic emissions and internal dynamics echo behaviors typically associated with these stellar wannabes. This has sparked discussion around the possibility of a new classification. Perhaps Neptune and similar bodies exist within a transitional category that blends planetary and substellar physics. Adding another layer to this enigma is Neptune's evolving atmospheric patterns. Its high-speed winds, often exceeding 1,300 miles per hour, are unlike anything else observed in the solar system. But rather than being driven by differential solar heating, like Earth's jet streams, new models suggest these winds may be generated by subsurface interactions. Imagine a planet where storms are born not from sunlight but from deep, internal convulsions. This means Neptune may be the only known planet where weather is birthed from within. If confirmed, this model could be revolutionary. It suggests a mechanism by which gas giants in dark orbits, with little solar input, could still maintain complex meteorological systems. Such a finding would deeply influence our theories of planet formation and atmospheric science, and could reshape our expectations for weather patterns on distant exoplanets. Perhaps the most philosophical implication of all comes from the realization that our cosmic backyard is still full of surprises. Tyson emphasized that if we can be so wrong about Neptune, a planet we've known about since the 19th century, what other misconceptions might we be holding on to? The truth is, our understanding of the cosmos is built on fragments, on brief glimpses and incomplete data. Every new discovery is like opening a window into a house we thought we had fully explored, only to find entire rooms we never knew existed. In this way, Neptune is not just a planet. It's a reminder, a symbol of the unknown, a challenge to our assumptions. Tyson's words echo like a call to curiosity. Don't look away just because something seems distant or cold or quiet. Sometimes, the most powerful revelations lie hidden where we least expect them. With more telescopes coming online and future missions under development, scientists are racing to explore Neptune in greater depth. There's renewed talk of sending an orbiter, or even a descent probe, to examine its atmosphere and internal composition firsthand. The urgency is real. Neptune is no longer the final stop on a planetary tour. It has become the gateway to a deeper understanding of how diverse, complex, and surprising the universe truly is. As our tools improve and our models evolve, Neptune will continue to whisper its secrets through faint radio signals, strange magnetic pulses, and deep blue swirls of cloud. And those whispers, long ignored, are now impossible to unhear. We thought we understood Neptune. We thought we had mapped the outer edges of our own solar system. But in truth, we were only scratching the surface. The final frontier might not be light years away. It might be hiding in plain sight, right here in our own cosmic backyard, waiting for us to open our minds and look again. What else lies beneath those clouds? Only time and courage to keep asking will tell.